when an event is almost certain to happen, now some of you got a little confused on this yesterday. Its complement will be an unusual event. Give me an example. Who did I do this with yesterday? Thank you. Dan? Give me an example when something is certain and its complement will be unusual. Okay, so say it is going to snow today, and they predict it to be almost 100%. They predict it to be 90%. What's its complement? It's not going to snow. And what would that percent be? 10. So would that be less, more unusual if they're predicting a 90% chance of snow? All right, so a complement is 1 minus that. So if one is high, the other one has to be low. And vice versa. If you want to stay in the middle of the road, you pick 140%, you pick 160, and you're kind of smack in the middle. All right, so were you able to match these guys up? Now, remember your tree. And you toss a coin. This is you tossing a coin, heads or tails. Put your probability right on your stem. And then you're selecting a number 1 through 9. And these are 9 of them. Each one is 1/10 from 0 to 9. You've got 10 digits from 0 through 9. Multiply across your stems. 1/2 times 1/10. There's your 1/20th. You could also judge which one has a higher probability just by looking at it. Like for B, that's got to be probably the smallest one. The next one. That has, you can't find that. So there's your 0. There's your uncertain. There's your impossible. Your game show. This is the one we talked about, the Monty Hall type one. Excuse me, where they pick a door, and when he takes one door away, then her probabilities will change. So if she has 4 doors to choose from, each one is going to give her a 25% chance of getting that right. Good so far? Okay, was everybody good with the tree? Can you do the tree? Does it matter which way I do it? Can I do the RH first and then the blood type? Sure, either way. What's this called when we multiply? What principle is that?
Fundamental counting.
Fundamental counting principle. Do the fundamental in there, good. That's your counting principle. Do your counting principle first, because then you're going to know if your tree is good. Right? Oh, I thought you had a question. All right. You had to decide if they were simple or not. Any problems with that? Simple yields how many events, how many possible outcomes? 1. If it's not simple, it's more than 1. Good. Your counting principle, everybody go with that? Okay. Even though they use a 12-sided die, it works on the same principle as your 6-sided die. So you're going to take the same probabilities here. Instead of 1 out of 6, you have 1 out of 12. If you're looking for numbers divisible by 3, write out your numbers, count which ones are divisible by 3. Is 1 divisible by 3? No. Good. Good. And finding your empirical probabilities, these are your experimentals. That's what we're about to do in a few minutes, your law of large numbers. You're going to find your empiricals. You're using this as a forecasting tool. Everybody good with the 3 decimals? Yes. 3 decimals because sometimes probabilities are percents. So if you went with, say, like for instance this one, you got 26%, but there's always a little bit more. You want to be as close as you can. We don't want to really string out like 5 digits, but if we do 3, rule of thumb, you at least get a decimal in your percent. So you know it wasn't exactly 26. Yeah, good question. Most folks go rule of thumb 3 decimals. All right. Types of probability. Everybody okay with those? No. So which one? 41. According to company records, the probability that a washing machine will need repair during a 6-year period is 10%. Will that change over time?
Yeah.
Like if I do this in another year, Aaron, will I still get the same probability? Will it be 10%? So that's your experimental part. Even though you're not experimenting with that washing machine, that's your company records, your count. That hasn't been proven over time. Over time would be my washing machine never, ever, ever changes. It's been proven over time. Very few things are theoretical. The probability of choosing 6 numbers from 1 to 40, this is not going to change. You're still getting one winning ticket. One winning ticket out of how many you sold. And we said the other day, if you sell less tickets, does that improve your probability or decrease your probability? If you sell less tickets, increase your probability. Increase your probability. Good. We hate this. They lost my light bulb, blew out, and they haven't gotten me a light bulb, and this thing stinks. But they try not to laugh at me too hard. Okay. All right, everybody okay with that? The complement condition. The 1 minus 47. 47 and 49. Did I give you both? Yeah. The 1 minus. It's much better than having to add up all the others. The table's not that large, so you can still do it the other way. But if you had a table with 100 entries and you wanted everything but 1, you wouldn't want to add up 99 entries. You would take the total, which they usually give us the total frequency, and subtract yours. This is your complement. Remember, it's an E, not an I. Yes. The 173. Because we said you're looking for who is not 15 to 29 years old. And the not 15 to 29 years old is 20. So we take 20 away from your total, and we build a ratio, part of the whole. Use your not, and that saves you from adding the rest of the table up. And again, there weren't very many entries, you could do it. Were you guys okay with your tree? Most of you had this tree yesterday complaining it was a little large. Yeah, it was a little large. Do your counting principles first to make sure you know how many you get. If you see a pattern, go right for your sample space. If you see that this is columns 1, 2, 3, 4, 5, and you've got colors for each one, go right to your sample space. Start your tree, and as soon as you see it, just cut to your sample space. And do your probabilities off of this. Rolling a 5 and landing on a blue, that has to happen at the same time, the ands. So only one 5B we get, 1 out of 24. Rolling a number less than 6, and the spinner landing on yellow, well, your less than 6 are all your 1 through 5s. Go to your yellow, and you got 5 of them. 1, 2, 3, 4, 5. 5 out of 24. Remember your bottom number is what you found in your counting principle. Your access codes? Good? Everybody good with the access code? Lay out the lines, like we did the other day. The probability of not selecting it, here's your complement case. Use the 1 minus tab. This one? 1 minus 0.001. Or you could do 1 minus 1 over the 1,000, either right over. The access codes consist of a letter, 26 possible letters, followed by 4 digits. Lay them out. Any letter can be used. The first digit cannot be 0. So you got 1 less, no 0. And the last one, even. 5 out of 10 are even. 0 counts as even, because that's the 10, technically. Good. And the last one. I kind of like this one because a lot of you do this in your biology ones. Those squares, and you figure them out. We talked about making equal probabilities. So you had your pink, your red, and your white. Remember, the pink took up 2 boxes. So that was half of your chart pink. Good? Questions? No? Okay, so that's your fundamentals. So let's figure out how we can experiment and toss a coin and come up with your law of large numbers. We're going to see your experimental probabilities reach your theoretical probabilities, hopefully. Why did I say hopefully?